Two very important topics. One is writing to an LCD panel, and I have some example code that I want to help you trace through. And so we're going to do that in a variety of ways. I'm going to show you the code. I'm going to show you some things from data sheets, and then I'm also going to actually show you what that does on the screen. So I posted some sample code. As we're going through, I want you to know where you can find this sample code, because you're going to use that to complete an in-class exercise. So if you go to the modules section on Blackboard, or not Blackboard, Canvas. I've been teaching so many years in Blackboard I still sometimes refer to it that way, but on Canvas. And we're going to need a few of the files that I've posted here. So we will be looking at this Explore 8 User's Guide. That will give us some information about the schematic of how the LCD is connected. You're going to need this MCP23S17 datasheet. That's an I/O port expander. And then we're also going to get into the second datasheet for the LCD panel. And so those are going to be some references. I'm going to go back and forth. So you may want to just go ahead and open those up so you have them in front of you, or you're welcome to just know where those are and follow along, and you can watch this video later. The in-class exercise we're going to do today is in-class exercise 6. So we'll talk about that later on once we explain this code. And then the code example that I'm going through, I have posted as a zip archive under LCD example code. This is under the module interfacing with external devices. So I put that right below the lecture that you hopefully watched for today, the first one, which introduces how to write to the LCD. Okay? Can everybody hear and see my screen okay? Okay, good. All right, so let's go ahead and go through this code. And the first thing that I'm going to do is simply show you what this code actually does when it runs on the board. And so in this case, I have a little document cam. And what I've done is I've written code that I have programmed the board to simply display ECU electrical engineering exclamation point on 2 lines of the LCD. And it takes a fair bit to understand exactly how that happened. So let me go ahead and unpack that code for you a little bit. So I'm going to go ahead and minimize this, get this off of the screen. And what I'm going to do is I'm going to bring up MPLAB-X and show you the example code. So let me drag this onto the screen. And so what I have done is actually created a project using the files that are in the .zip archive that I posted on Canvas. And so in this area under headers, I have put 4 header files that if you expand the zip archive, you will find those 4 header files. And then under source, I've put 5 .c files. Yes, this session is being recorded. So I'm not recording it within the Canvas conference. I'm recording it using Camtasia, and so I will post this whole full screen. If I just recorded it this way, it would only record, basically what we have, and it would go away after 2 weeks. But because we're covering so much in here, and you're going to be using a lot of this the rest of the semester, I wanted to make sure I did a full screen recording that won't go away after 2 weeks. Okay, so recording this, and we'll see this as we go on through. So in this case, if you wanted to make a project just like this, and you're going to do this in your in-class exercise, you can just unzip the archive that I've provided and put these 4 files right in here and these 5 files down in here. Now a lot of these files are very similar to what we used in Lab 1. So in Lab 1 we had a whole lot of different files, and it was basically just an overall demonstration of the capabilities of the board. And at that point, we did not really drill down to try to understand exactly what was happening in that code. And so that initial demonstration did a lot of different things. So it could do analog to digital conversion, it put things out on the display, it blinked some lights, all those kind of things. So what I've done for this example today is I've really pared down some of that code, and I've given you some files that allow you to exercise the LCD panel. I've eliminated a lot of the other files, and I've put some changes in this code so that you don't need that MCC generated file. So a lot of this was actually generated through the microchip code configurator, which is from up here, the MPLab code configurator. And so what that will basically do is automatically generate some code for us. So a lot of this code was not anything that I developed myself, so I'm going to give credit to Microchip. Some of this I have modified to fit the needs that we have here. I've taken out some code that was really unnecessary for purposes of this demo, but I've left a lot of other things in and just modified things as I saw fit. So the main file is going to be in this eeswag.c. And so this right here, you have your usual disclaimer. Then up here we have our configuration bits. Nothing really surprising here. So these are modified slightly from what I had given you before. And then we have to include two files here. We're including two of the header files. One is mcc.h. That is to use some of the things that the MPLab code configurator developed for us. And the other is lcd.h, and that is so we can use some of these LCD routines, which I'm going to go through in a little bit. Then we get into our main function, and our main function calls a few other functions. It calls this system initialize, and that is in mcc.c. So what I want you to notice over here is that there is a pairing between .h files and .c files. And so, for example, if we go into mcc.h, you'll notice in here that I have actually modified this from what the MCC initially gave us. So I don't need the device config, I don't need this interrupt manager, I don't need these things about timers. A lot of that was just built in when we automatically generated this from the MCC. We're not using that in this example, so I've just commented those things out. But we are going to use the pin manager. We'll see that in just a little bit. Here you'll notice we're defining our crystal frequency as 8 megahertz. So we have the 8 megahertz crystal oscillator. You should be familiar with that. And that's largely because, as you'll see later, we're going to be using some of those delay macros that we used in the music lab. And then we get into this system initialize, oscillator initialize, and watchdog timer, or WDT, initialize. You'll notice that these are not the function implementations themselves. These are simply function prototypes. So what they do is they say there is a function named system initialize. It doesn't return a value. It's a void function, and in this case, it does not take any arguments, so we explicitly put void. This function is actually defined in the companion file mcc.c. So if we open up mcc.c, now this actually shows what system initialize does for us. And so system initialize calls pin manager initialize, oscillator initialize, and SPI initialize. And you'll notice that I've commented out these other initializations. That's largely because we're not doing in this file analog to digital conversion. We're not using any PWM. We're not using timers. I'm strictly doing this just to initialize the pins, to initialize the oscillator, and to initialize the SPI, which is this serial interface. So we're not going to get too much into exactly what's happening in serial here, but I just want you to know that we are using the serial pins. We'll have much more detail talking about serial communication later on in the course, but we are going to need to use some serial communication in order to talk to the LCD. And so we're doing some initialization in here. So this oscillator initialize just really initializes some configuration for the oscillator itself. You don't need to worry too much about that. This is initializing the watchdog timer. We're not calling that because we're not using the watchdog timer. And then if you go over to pin manager initialize, so the prototype for that is up here in pinmanager.h. So we see a lot of different definitions. This is just defining some little inline commands. But if we go here into pinmanager.h, you'll see that there is a prototype for the initialize. And then if we go down here to pinmanager.c, the actual initialization is happening here. And so there's a lot of different things happening in here. This writing to the latch registers is basically just zeroing out all of the ports. The tris registers, as you're aware, they make things inputs and outputs. So this is kind of the default setting for some inputs and outputs. We have our AND cell registers. I didn't configure these myself. Typically, I would just make everything digital unless it's explicitly analog. But in this case, they were using some things as analog, some things as digital. We haven't talked about these weak pull-up registers, but this is basically just disabling weak pull-up so that we can just control pins directly. You don't need to worry too much about that. And then this is talking about open drain configuration. We're not really using anything other than the default. That really just gets into some of the voltage settings on the pins. And then we have some other settings here. A lot of these are just defaults. And then down here, this is the interrupt on change. We're not using the interrupt on change in this case. So we're clearing out the flags. We're not worrying about that. These are just a lot of default initializations, some of which are useful to us, a lot of which are really just not. So since I'm calling that function, I did want you to see that that's what's happening, but we're going to focus our attention on these LCD routines. So we're calling the system initialize, and then we get into several different LCD commands, and these are all implemented in lcd.c. So that's what I want to focus the first few minutes on, understanding the LCD rights. So the system initialize is critical because we have to set up some inputs and outputs, and I will showcase what specific pins of the microcontroller are involved in writing to the LCD in a moment when we go through the schematic. But then I will also go through, so really we're just setting up things as digital and things as inputs and outputs on appropriate pins. Then we initialize the LCD, and we'll go through that routine in some detail. That's basically just setting up how the LCD will function. And then we have this LCD go-to routine, and this is going to a specific row on the LCD and a specific column. So this first line, LCD go to 0, 0, just makes the writing position the top left. And then we're writing this string, so this can take in a whole string argument, and it puts it out one character at a time. We'll walk through how that routine works. And then it's going to 1, 0. So the first line is line 0, the second line is line 1. So this is advancing to the second line, the first column of that second line, and then we are writing out engineering on the second line. Then what I have down here at the end is an infinite loop, but you'll notice this semicolon right here. What that's basically doing is it's an infinite loop that does nothing. It's just sitting there and holding forever. So the semicolon just means this is a hard wait, and the while one will always execute. If I don't put this here, what will happen is main will run all of its code again in an infinite loop. And what that will do is it will go through some initialization, it will initialize the LCD, and then put this out. And that will basically just make my display flicker. So because it's going to go through clearing out the LCD and then rewriting the letters every single time. I don't want to have to bother doing with that, so I'm just going to write it out and then I'm just going to wait just so you can see exactly what is on there. Okay? So before we get into the rest of the code, let me explain the hardware that is being controlled. And so I have the data sheet open, the Explorer 8 User's Guide. And so let me pull this up. So in the Explorer 8 User's Guide, this is page 40 of that User's Guide. And I had some screen capture of this in the video lecture that I posted. This shows the schematic for both the LCD connections and this external I/O expander port. So let's talk a little bit about what's happening in there. Let me zoom in just a little bit on this. And so first of all, let's look at the LCD over here. As you hopefully saw in the online video lecture, the LCD takes in parallel 8 bits, and those 8 bits can be either instruction or data. And so if they're instruction, they can do things like telling the LCD that you want to see the display cursor or you don't want to see the display cursor. You can say I want to use both lines of the display or only want to use one line of the display. You can blink that cursor or not. Or if you're talking about data, you can say I want this specific character written out to the LCD. So that's where either those commands or the data are written in. And then over here, hopefully you saw that E is our enable bit. That's effectively a clock. And so this is a sequential logic device, meaning that we are clocking in those commands. And so we need a rising edge of E in order to put in either the data or the command. RW allows us to either read from or write to the display. But as you notice here, this is hardwired direct to a pull down resistor to ground. So what that means is we're always in write mode here. We are never reading back from this LCD. So that's a little bit of a limitation on the Explorer 8 hardware, is that you can never read from a display. So you could imagine some industrial applications where maybe somebody's typed something in on a keypad and now that's on the display. You might want to read in what their entry was. We don't have that capability here. All we're going to do is actually just drive text or symbols out to this display. So we are always in write mode here. And then the RS bit is what determines whether we are sending commands or we are sending data. So if you want to put the next character out there, that is sending data. If you want to do something like clearing out the display or changing how the cursor appears or doesn't appear, that is a command. So in the old trainer kits that I used with students up until this academic year, all of this was directly hardwired into the PIC. And so port A was used to control these three lines, and then port D was used to control these. Your trainer board that we are using, the Explorer 8, actually uses an external chip to do a little bit of conservation of pins. So you can see if you needed to hardwire all of this to your PIC, you have 8 bits for these data lines, and then you have another 3 bits. That requires 11 pins to be able to send that information. What we are going to do instead is some serial communication. And so over here, what we have is serial data is going to come in on this SI, that is driven by pin RC5, and then this serial clock is going to paste that in. That's coming in on RC3. And then we have RA2, which is acting as a chip select. So that's allowing this data to be clocked in. And then effectively what this I/O expander does is it gives us 2 additional ports. And it gives us those ports on a bank of port A, which is GPA here, and GPB. This is not to be confused with your port A and your port B that are internal to the PIC. These are effectively taking in serial data. These are little shift registers that are one at a time putting in the data until it's fully lined up. And these are, as you see here, port A is connected to our E and our RS pins, and then port B here is connected to our data lines or our command lines. And so that is what we have here, and then we can reset this with RB5. And so if you were to go back and look at the code, those tris registers are basically just setting these things up as outputs so we can control this. So understanding that hardware, now it's important to also look at how this particular device works. So in general, what we're going to do is send some information in through this serial input, and we're going to clock that in, and we're going to put some things onto these 2 registers. And so if we look at the data sheet, I've also posted the data sheet for this chip. What I want you to see here, this is on page 12 of that data sheet. And in this case, it has its own registers. And there's really only going to be 4 registers that we're going to be dealing with for purposes of the LCD. That is the IODIRA, IODIRB. So just like what we have to do within the PIC, those 2 registers indicate the input-output direction of port A and port B. So we're going to be using those strictly as outputs. Again, we're not reading anything back from the LCD. We're only writing to it. So we're going to use those 2 registers to write to the LCD. So we have to configure our ports as outputs. And then down here, GPIO-A and GPIO-B, that's where we're actually going to put what we want. For GPIO-A is going to be where we're going to put what we want on RS and E, and then GPIO-B is where we're going to put those commands or instructions. So let me pause just a second. I see Robbie has a question in the chat. He says the GPAs operate port B, which controls instruction on data and clock. Then port B controls, yep, that's exactly right. So what you write to GPIO-A here, that's going to control the RS and the E. And then what you write to GPIO-B, that's going to control the DB0 through DB7, which is what specific instruction or data are you actually writing out. Okay, so I know I just covered a fair bit of information. Before I go on, are there any questions thus far? Okay, hopefully everybody's tracking now. Let's get into our code here and see what is actually happening in terms of those registers. Okay, now before I do that, let me also show you the data sheet for the LCD itself. So I posted two different data sheets. This is actually the second one. This is the much more detailed one. And in this case, what I want you to scroll down to is looking at the instruction set. So if we scroll on down here, I should have queued up the right page. Pardon me. When you get onto page 10, what this shows is the initialization sequence. So we're going to go through effectively this, but if you go to the very next page, this shows you what those commands are that you can write out to the input pin. So if you're talking about commands, it also tells you something about how long it takes to execute these. So that will inform our delay. So we're going to send in these instructions, and then we're going to delay for a little while just to make sure all those instructions get on through. So you can do things like clearing out the display. That's going to effectively just overwrite all the characters that are currently on the display with 20 hex, which happens to be the space character. So that's just going to make it look like you cleared it out, when in fact every character that's on there is in a RAM location, and because there's RAM built into the LCD, and what you're effectively doing there is just writing over all the contents in RAM with the ASCII key character that corresponds to the printable space. And so it just looks like you're blanking everything out. All you're really doing is replacing things in there. You have a return home, which is basically a way just to put your cursor up to the top left. And then we'll unpack some of these others in terms of their display mode setting and function set and those kind of things as we go on through. But just know these commands are here. And so let's go ahead and start looking at what the code is actually doing, and then we'll walk through these commands as we move on through. So the first thing that I want to go through is this LCD Initialize Routine. So I'm going to go into lcd.c, and you will see a few things right here. The first thing is it's calling LCD Write IO Expander. So what this is doing is it's effectively writing a value out to a specific address in that IO Expander chip. And it's going to write that using serial communication. And in order to do that, it needs an address of a particular register, and it needs the data that you want to write to that register. So these first two commands, you'll notice, are writing to IO_dir A address, which is, I've added these comments since I posted that. So if you don't have these comments, this might be a good time to add them in your code. What IO_dir A, that is the directional address for port A. And so if we go back to the data sheet for that IO expander, right here, you'll notice that that is this first address. We're using the iocon.bank 0. So this is 0 location is for A, and then 1 location is for B. And what we are doing is we are writing output direction. Now output dir is defined as a constant right here. And so what this does is it says whenever I type in output underscore dir, I want you to replace that with zeros. And so putting zeros here is effectively the same thing as putting zeros into the tris registers in the PIC. It's making those bits act as outputs. So our I/O expander chip can actually behave as input or output. We've effectively gotten ourselves two more ports, two more 8-bit ports, and in this case we want to make them outputs. And so these first two lines are just making port A and port B on the expander outputs. Now what we are doing is we are actually writing to GPIO A address. So this is writing what we want out to the address associated with port A. So if you look, GPIO A address is actually defined, I believe that's defined in our lcd.h. Let me see if that is the case. Yep. So lcd.h is where these are defined, these addresses. So we have address 0 and 1 for the directional addresses. And then GPIO A address is hex 12, GPIO B address is hex 13. And so if you go back and look in the data sheet for that I/O expander, you will see that 12, hexadecimal 12, is the GPIO for A, hexadecimal 13 is the GPIO for B. And so effectively what that is doing is, now that you have made these pins all outputs, when you write to the GPIO address for A, now you're saying, here's what I want on E, here's what I want on RS. And you'll notice it's also, even though this isn't in the schematic, it's putting a 1 out here. We'll see that in just a moment. It's going to put a 1 out here on this pin, and that basically just enables the LCD to work. So even though this isn't shown in the schematic here, it is putting a 1 out on this particular pin. And so if you were to look at this, let's go back to our LCD initialization code. So we've made things outputs, and now we're putting LCD VDD enable. And so we see here, this is hexadecimal 20. And so let me shift around to my document cam for just a moment, and I will help you to unpack what's actually happening there in those registers. So let me move some things just a second, and I will bring that over. So let me bring this over. Oops, upside down. Let me turn my camera around. So effectively here, let me get my cord out of the way. All right. So our general purpose A register has RS is in bit 7, E is in bit 6, and then we have this enable, which is really not shown on the schematic, but that's bit 5. And then bits 4 through 0 are not connected to anything. And then over here on our general purpose register B, all of those pins, that's either the command or the data that you want to write to the LCD. And so those are the values that we are setting up. And so if we go back here to what's actually happening in our code, the first thing that we are doing is we are writing to GPIO A address, and we're writing LCD VDD EN. And so you'll notice that LCD VDD EN is hexadecimal 20. And so if we put hexadecimal 20 on top of these bits, let me pull this back up. What you're going to see is hexadecimal 20 would be 0010 0000. And so that is not putting anything other than a 1 on this bit 5. So that's really just enabling the LCD. I'm not putting anything over here on a command at that point. I'm really just turning on the LCD. So that connection is being made right there. Now let's go to our next command. And our next command right here is LCD function set. Now, you'll notice right here, this is not in the write I/O expander. This is being called in an LCD write command. So let's go down to our LCD write command function, and you'll see that right here. So LCD write command starts out and it writes to the GPIO A address and it writes hexadecimal 60. Then it writes to the B address and it puts whatever command we send, and then it writes to the GPIO A address hexadecimal 20. Well, let's see what that actually does. So if we go in here and we write 60, what 60 is going to do is it's going to be 0, 1, 1, 0, 0, 0, 0, 0. That is putting a 1 on our E. And then we are putting in whatever instruction we want over here as a command into register B. And then the next thing that we are writing after that is hexadecimal 20. And so hexadecimal 20 will make this still a 1 over here on the enable, but that will zero out the E bit. So effectively we have a falling edge on E, and that is what's going to clock in our commands. So when we have a falling edge on E, that's clocking in things. You'll also note that this is setting up a 0 on our RS bit. And what the 0 there means is this is an instruction. This is not data that's coming in. So every time I want to write one of those commands to the LCD, what I'm going to do is I'm going to put the command that I want into port B, and I'm going to go through this sequence of basically just writing to the external port A, this 60, write the command to B, and then I'm going to make the E low, and what this is doing is effectively taking a falling edge of E to clock in that command. And so every time I want a command, and that command can be really any of the things that we have in the data sheet here. It could be any of these. I'm going to set those up in port B, and then I'm going to clock it in. And so the first command that we have there when we're writing a command, if we go up here, is our LCD function set. Okay? So LCD function set, if you look just above, that is defined as hexadecimal 3C. Okay? So we see that right here. LCD function set is defined as 3C. So let me go ahead and switch back over to my document cam here and show you what that's actually doing. So in this case, we have hexadecimal 3C. And so this first bit indicates that is the function set. This is second bit here is now indicating that I want 8-bit mode. So the LCD can actually take in commands in either 4-bit chunks or 8-bit chunks. Because we're using 8-bit, we need to put a 1 right there. And then this N bit is meaning that we have 2 lines. We're using both lines on the LCD. And then this bit is actually determining how the pixels are going to be arranged. So you can choose to have a different basically matrix of pixels to display things. You can choose more or less pixels. And so in this case, we're choosing more. How did I know that this is what's happening? Well, I really just went through the data sheet, and it's kind of a search and discovery type mission in there. So if we have 3C, I know that 3C is 0, 0, 1, 1, 1, 1, 0, 0. And so to find that, what I'm going to do is look through the LCD data sheet right here and really find a pattern that starts with 0, 0, 1, 1. Now, if you look at this particular table, let's go up to the top. When we're talking about that 0, 0, those are going to be in DB7, DB6. These other 2 bits are just about whether these are command or whether we're reading. In this case, all of these are commands in here. So ignore these first 2 columns. And we're just looking for something that would start with a 0, 0, 1. Well, that can't be clear the display, can't be return home, it can't be entry mode set, can't be here. And so we keep going down, and now we see this 1 right here. So because we start with 0, 0, 1, that could fit the pattern of a function set. And so then from there, we get into the DL, and this explanation over here tells us the things before the slash are what happens if you put in a 0. The things after the slash are what happens if you put in a 1. And so in this case, we're putting in a 1. So that means we want 8-bit mode. And then N, here we're putting in another 1. That says we want 2-line mode. And then our display font, this gives us a choice between whether we are using 5 by 8 dots or we're using 5 by 11 dots. And so we're just going to set up each of these blocks to display each of our characters as being 5 by 11. Okay? So that's really what's happening in that first command. Are there any questions on the function set? Alright, so let's go back to our code and let's see the next command that's being written. The next command is LCD set display. LCD set display is 0C. Okay, so if I go back and I see what's happening here, I'm going to put my dot cam to show that. And right here, I've parsed out and said, okay, 0C, that means that I've got a 1 right here. So that is a display set. I'm turning the display on. And then what I'm setting this up for is I don't want to see the cursor and I don't want to blink the cursor. So how do I figure out that that's where that's coming from? Well, again, if I go back to the LCD datasheet and I look for something that could fit the pattern of 0C, let's look for that in the datasheet here. So I need something that is all zeros for the first nibble. So there's a lot of things there, but then I need something that's going to have a C pattern in here, 1, 1. Well, that's not going to fit here. Here we go. So this is the display on-off control. So because I have a 1 here and D could be configured as a 1, then that basically tells me this is what I need. This is the instruction that I'm writing right here. So it's the display on-off control. This 1 gives it away. Then our D, we are putting in a 1, and our C and our B, we're putting in a 0. Now, if you go back up to the previous page, what this tells us is putting in a 1 for our D turns the display on, and putting in zeros for C and B basically turn off the cursor. And so if you look at what our code is actually doing on the board, you will notice that there is no cursor. You're not seeing a cursor, you're not blinking the cursor, but if you wanted to, you could put the cursor to indicate the current position, and then you could also choose to make it blink. So it's really just a personal preference of how you want your information displayed. In this case, we're not showing the cursor, we're not making it blink. So that's what's happening right there. Now, if we keep going through the code, let's go back into what we're writing next. And so that is setting the display. Then we go to LCD clear. So LCD clear is right here. That's a 0x01. And that is a very basic command which does exactly what I was talking about before, which is just putting a space out to every entry in RAM. So it basically just clears out the display. So that is this command right here. Then we go on to our next command, and that is LCD set display. I'm honestly not really sure why they're doing that again, but for some reason the default code that came with the board just does the LCD set display one more time. And then the last thing is LCD set Ddram address. And so LCD set Ddram address is 0x80. And so if we look for the pattern of 0x80 here in the datasheet, we need something where DB7 is going to be a 1, and that's all the way down here, setting the Ddram address, and then this is the rest of the address. The Ddram address is basically just, the Ddram holds the characters that are being displayed on the panel. And so if we make the Ddram address all zeros, so the 1 just says I'm setting the address, the rest of it says what that address actually is. If you make that 0, that is the address associated with the top left cell. So effectively what you're doing, if you go in to look at the board here, by setting it to 0, you're effectively initializing your location where you're writing your next character to this top left entry in the matrix. And so that's where you're going to start writing, and then you're going to write characters starting from there. And at any point, you can change your address to move around. If you just keep writing data, it will just increment to the next, the next, the next. But if you want to skip around, we'll talk about that in some upcoming commands. If you want to skip around, you can just use that command to change the address that you're writing to. Okay, so that is effectively what's happening as we initialize things. So that is doing the initialization. And so you'll notice these delays in here. These delays are just making sure that we are waiting enough time between writing those commands. So if you look in the data sheet, you'll see that it takes a certain amount of time for each of those commands to be executed. And so we are waiting that amount of time. In some cases, we're waiting maybe a little bit less just to make sure things are set up, because actually writing those commands does take a little bit of our time. So as things are being serially sent in, that takes some of the time. We're just waiting a little bit longer just to make sure these things are all settled before we proceed to writing the next command and potentially overwriting the previous command that we had in there. So that's initializing everything. Now, if we go back to our eeswag.c, we've called the initialize, so now we have a better understanding of what's happening there. Now we have this LCD goto 00. What the LCD goto routine does is it changes the location in RAM where we're writing to the first number is the row, and so the top row is row 0, the bottom row is row 1, and then it changes it to whatever column you happen to want to be in. And so 00 is the top left. Now effectively, this first LCD goto is not doing anything useful because LCD initialize already put us in that top left position. But in general, let's go ahead and look at our LCD goto. That is defined over here as well. And so if you go down here to LCD goto, it's a very short command, but there's something new in here that I want you to see in terms of what's happening. First of all, it says if row is less than 2, then do this. You notice if the row is not less than 2, it doesn't do anything at all. So the only rows that we have here are 0 and 1. If you try to say go to row 3 or go to row 2, it doesn't know what that is. That's off the display. So it's just not going to do anything. So row has to be either 0 or 1. You'll notice also in here the type that is passed is uint8_t. That is effectively the same thing as a char. It's an unsigned integer of 8 bits. And so we're passing in two values. One is the row and the other is the column. Now, what this is doing, this is effectively a C way to do an inline if statement. And so what this is saying is if row equals 1, that's what this kind of question mark equals, question mark with the colon does, is this is a condition, and then if that is true, then what I want you to do is do this. Otherwise, what I want you to do is do that. So this is effectively the same thing as saying if row equals 0, then do this. Else do this. So it's a very short form way to do this. And actually what we're doing is putting that into this. So this would be what you would have to do. And we couldn't actually, I don't know that we could write it exactly this way. You would have to declare the value and then assign it right in here. So you would declare it earlier. Excuse me. So you would have something like this, where you would declare this, and that's basically a position variable. And then down in here, you would just say position is equal to that, or position is equal to this. So this is a very elegant solution where in a single line, it's declaring a variable position, and that position is going to basically be either in the top row or the second row. And now what we're going to do is write that command down here. So we're using that write command, and effectively what we're going to be creating in here is going to be a command just like we just saw in the last part of the initialize, where we're basically just changing the Ddram address. So let me go ahead and take this out. This is effectively what this one line is doing. Now, further elegance in here is it's doing a bitwise ORing in here. And so let me show you exactly what is happening here. It is starting with the line 1 start address or the line 2 start address. So depending upon whether you're talking about row 0 or row 1, let's go to row 0 as a starting point. Let me walk you through what that code is actually doing. So if you start at row 0, it is starting you with a baseline of line 1 start address. And so if you go up here, this is actually defined earlier in code. Line 1 start address is started out as hexadecimal 80. And so let me put that on the document camera. So hexadecimal 80. And that's going to equal 1, 0, 0, 0, 0, 0, 0, 0. And then what you're doing is you're ORing in the value of the column. And so if we were to look at these as, let's say, 2 rows, you've got more than that, but effectively you've got 16 columns in here. This is going to be memory location 0, this is memory location 1, this is memory location 2, 3, etc., all the way across. And so your column is going to be starting at 0. So this is row 0 or row 1, and then your column could be 0, 1, 2, 3, etc., going all the way across. And so what we're doing is we're doing a bitwise ORing with our the address that we want to put in here. So we're ORing our default baseline. This is the baseline of the leftmost top row, and then we're putting in which column offset that we want in here. So that's what this bitwise ORing is doing down here in the goto. So in this case, let's say we wanted to go to column 4. What we would do is start with this, and then 4 would come in, and so we would put in binary for 4, and then we would do a bitwise ORing. And this is what we would get. And when you write this to the Ddram address, that becomes the new Ddram address, and so that's going to put us in memory location 4, and that's going to point to this column. If you wanted to go to the second row, the first entry right here in the second row, then that, if you go up here, starts with C0. And so C0 is just this. And remember, this is the address. So it's really starting at 40 hex right here, and then this will be 41, 42, etc. And so if you wanted, say, the third column of, or column 3, which is really the fourth column over because it starts at 0, then you would just do a bitwise ORing with 0x03. And you would ultimately write 1100, 0011. And writing this command, this says replace the Ddram address. Oops. Somehow I'm not showing you my work here. I apologize. So this is showing C0. And that is the first line of the second row. And so what I was saying is that is memory location 40, 41, 42, 43, etc. And so if you wanted to be in column 3, which is really the fourth column, you would do a bitwise ORing of C0, which is the baseline for the leftmost, and you would OR that with 3, which is your column offset, and this would be the command. The 1 says change the address in the Ddram that you're writing to, and then this says here's what the address is that I want to go to. Okay, so let me see if I can pick up some questions in here. You did not see the eeswag.c file in the code? Yeah, if you open up the... so eeswag.c, it's not in the code for the first lab. There's a new zip archive on modules. So if you go into the canvas here, let me see if I can showcase that. If you go to modules under canvas, let me pull this over here, and you scroll on down to interfacing with external devices, it's in this zip archive right here. So that all the code that I'm talking about today is from this LCD example code.zip. Okay, so that's where that is. Let me check the other questions that came up. Let me pull this back to my other screen. Let's see. Whoa, Simon put in a long command here. Comment. Let's see. All right, so saw that. Yep, Simon was trying to answer Robbie's question. And then I think he gave him the code here. Okay. So you have it in the file, but it does it just not show the same as what I have here? I think you might have the wrong zip archive, Robbie. So there shouldn't be a labs in there. Yeah, I think you may be pulling in. Now, this is modified in many cases from the Lab 1 files. Yeah, if you want to share your screen, that's fine. I think I may need to stop sharing my screen for you to do that, but let me do that. Yeah, if you want to share your screen. Now, keep in mind, that's going to share with the whole class. So I just always like to warn people that just in case there's something you don't want everybody to see. Well, we may just need to talk offline. I'll have some time, hopefully after I get through all this, just to discuss things. But hopefully we'll just keep going through this, and then maybe you and I can individually just chat about it. All right, so let me share my screen back out. Is everybody else able to see that file and see the code that I've gone through? Okay. All right, so this is what these go-to commands are doing. And then let's go through the rest of our LCD commands. So we've talked about the LCD initialize. And then we've talked about the LCD write IO expander, which is basically just writing to the specific registers within the IO expander chip. The LCD write command takes a command and puts out 60 and then 20 on the A address, which basically just says RS is going to be low, and then we generate a falling edge on the E. So we have falling edge enabled there for the LCD, and we put in the command. We have an LCD write byte, which is effectively the same exact thing as LCD write command. Oh, I thought I had reshared. I'm sorry. Let's see. It should be coming up. I've got a spinny ball on my end. Hopefully it comes up in just a moment. Can you guys see my screen? Okay. So you see the write command and the write byte? Oh, you see arrows. That is not what I'm trying to share. Let me see if I might need to stop sharing and then reshare. Let me try stop sharing, share my screen one more time. There we go. Now can everybody see it? Okay. So Canvas conference was a little bit slow to show that. So we're back here. So the LCD write command, as I was saying, we went through that before. That's basically just putting 0 out for RS to indicate that it's command. And then it's setting the E bit and enabling the LCD. And then it puts the command out on the B port. And then it effectively writes the same thing, but in this case now lowers the E, so it creates a falling edge on the E clock, and so that clocks in that command. LCD write byte is exactly the same. The only difference here is now the RS bit is going to be high, and so when you're writing a command, you put RS low. When you're writing data, so writing the next character out, you want RS to be high, and so if you were to put these bits out, everything is exactly the same on A, except now RS is set, and instead of writing a command, you write data. So that's what's happening there, the write byte. Now we have this LCD write string, and what this is going to do is this takes in an array. So effectively, a string is considered an array of characters. And that array of characters can have as many letters, numbers, whatever as you want in there. And the last character is a 0. So if you were to look back at our EE swag, the first thing that I'm writing with this LCD write string is ECU electrical. And effectively what that does is it's creating a string, and the first character is going to be a space. Then the second character is going to be an E, and then the next character is going to be a C, and it's going to keep going all the way through until, I'm going to make these comments so it doesn't try to process this. It's going to keep going all the way through until I get my L character, then I get a space character, and then you don't see it explicitly written here, but when you put these quotes around it, the last thing that a string has is what's considered a 0. This is also known as a null termination. So a string is ended with the null character. That is implicit when you write things within quotes like this. And so if you use the LCD write string, you can explicitly write out things, but just know that the last character that is in here is going to be, by default, a null or a 0. So if we go in here to lcd.c and we try to write a string, what it is effectively doing is it's starting a counter at 0, And this is iterating through the array that is that string, and it's starting with the 0th. So in this case, what that's going to be, the 0th entry is going to be this space that I have here. Then 1 is going to be the E, 2 is going to be the C, 3 is going to be the U, and it's going to keep going. It has this little while loop that is basically just keeping on going until data hits a 0. So this while, what it's doing, when you just have while with a numeric, you're not saying less than or greater than, it's going to keep running until it gets the value of 0 inside of those parentheses. So if you give it a value that is anything other than a 0, it'll keep running that loop. But as soon as it hits that null termination, it's going to quit doing this. And what it's doing inside of this loop is it's doing LCD write byte. It's calling this to put out the next data, the next data, the next data. And you'll notice in here it has I++. So this line is not only writing out the next data, it's also at the end of it incrementing the I value. Now, it's important to note in C, I++ is a post increment. What that means is go ahead and pull in what the value of I is right now and then use it. But after you're done with this command, I want you to increment it after the fact. You can also do ++I, and what that would do is that would increment I before you pull it in. So that would increment it onto 1 before the first time it's pulled in. So in this case, we want to start at 0 and just keep going on through. And every time we go through, it's incrementing this. So effectively, this is another shorthand. You could write this as this, and that would effectively just increment it. And remember, I++ is short for I equals I plus 1. I equals I plus 1. So effectively, they're doing both of these lines in a single line by just saying I plus plus right in here. So this is just writing every character that you have in that string all the way across until you hit a null. And that's starting at whatever the Ddram address is that you're currently pointing to, and it's just going to keep going all the way across. Okay, so that is the LCD write string. We already talked about the LCD goto, and then the very last command, which we're not actually calling in our code, but which is quite useful, is an LCD clear. And all that LCD clear does is it writes the LCD clear, which just puts the space character everywhere, just wipes out your display, and then it goes to the top left entry point. So if you've displayed something and then you're ready to clear out and go on back and write something new, this basically just initializes your display back to cleared out and going back to the first entry point. So that basically shows you the LCD commands. That shows you how this code works. I know I've talked about this for a good bit of time, but I did want to make this interactive. I did want to record everything for you, so you'll be able to review this later. Are there any questions, anything that's unclear about how these LCD routines work? So where in the code did it mention the void or industry? It didn't explicitly mention it, but what's happening here is when I put in this, say, double quotes around anything, it's effectively creating an array of characters. And that array of characters puts in entry 0, that's going to be this, and it's going to keep going. This will be my last regular character, and just the way that strings are handled inside of C, the very next character that kind of terminates that string is just a null termination. And so the program knows about that. So what's happening right here is this while data I, it's just keeping on going. So if you say write a string, it's going to keep parsing, which means pull in the next value of that string until what you put out is a 0. So it's going to keep writing the next byte, the next byte, the next byte of that string until it hits that null termination. Does that make sense, Hassan? Okay, good. Any other questions? 0 and null are effectively the same thing. Yep. So when you hear null, it means it is a 0. And just to be clear, that 0 is not printable 0. So the ASCII value to actually display the number 0 on the LCD, that is hexadecimal 30. In this case, when we're talking about a null character, we really mean that the ASCII value is literally 0. It's not printable 0. It is literally 0. So if you wanted to print out 0, 0 can be part of the string, but that just gets converted into ASCII as it gets written to the LCD. So what's actually happening in here, when you write each of these things out, the space here gets translated into the corresponding ASCII. So space is 20 hexadecimal in ASCII. And then you go on to, okay, what's the ASCII for capital E? What's the ASCII for capital C? That's what actually gets written into that array. And then at the end of the array, there is a hexadecimal 0, which is the null termination. But if you actually had a printable 0, like let's say I said ECU electrical 0, if I wanted to physically print out a 0 on the display, this is not a null termination. That would get translated into hexadecimal 30. And we'll actually use that in the lab that we're going to do tomorrow. Yes, so this is kind of a personal programming preference. When I was taught to code, we didn't put void in the middle of that, but writing parentheses void is just an extra explicit way of saying I'm not going to give you an argument. There's nothing that's being passed to that function. So you can write your void main exactly this way, or you can take out the word void. It's really just the same exact thing. That's, again, one of those programming preferences. Any other questions? All right, so that's the first part of the lecture today. It seems so weird with these blocks. I'm packing two kind of major bits of material into this same lecture. So the first thing that I wanted you to know for today is how to write to the LCD and understand this code. I'm not going to spend nearly as much time talking about the analog to digital conversion registers because I think that's covered fairly well in the lecture. Are there any questions on the analog to digital conversion lecture that I could answer for you? All right, I don't see any. Let me go ahead and show you the in-class exercise for today, just so everybody is clear on that. So let me pull that up. So if you go to in-class exercise 6 under the modules, you will see that I have that. Let me put that onto the screen. So the first two things that I want you to do in the in-class exercise are simply modifying the code that I gave you. And so the first thing is modify the code so that you write out your name centered with your first name on the top line, your last name on the second line. Now, there is not, as you hopefully saw, there is not an explicit command to say center, left justify, right justify. Effectively, all you need to do is one of two things. You can either write a string and put before your name spaces to basically space it over. So just keep in mind that you have 16 characters all the way across. So depending upon how many letters are in your name, you might need more or less spaces to center that up. Or you can use the goto command and just start writing your name after you use goto to skip over. So that's something you can do. So just use those go-tos or use spaces, and you can just modify the code to put your name, first name on the top line, last name on the second line. Should be a pretty quick modification. Run that. You should be able to see that work on your LCD, and just save that as name.c, and you can upload that. The second thing that I want you to do with this code is modify it so that the first line just prints out press the RB0 button. And then what I want you to do is have the code wait until the RB0 button is pressed, and then upon pressing RB0 you should move to the second line and output thank you. And so what you're effectively doing is creating a wait. And what kind of a loop do you think you might use for a wait here? Yeah, if your name is an odd number of characters, just get it as close as you can to centered. It's not going to be perfectly centered up. So just kind of eyeball it. Well, you're very close, Simon. So Simon is saying use a while RB0 equals 0. Now keep in mind that the button that is connected to RB0 is actually going to output a logic 0 when it's pressed. It outputs a logic 1 by default. So, yep, you could put a while RB0 equals 1. And in that case, just be very careful when you're saying single equals. You want to do double equals, because double equals checks for equality. Remember, single equals is an assignment. So you could say while RB0 equals 1. That's one way to do it. Or the shorthand programmer way to do it is just to say while RB0. And so if you do that, remember, it's going to run so long as RB0 is anything other than a 0. And so it will stop running that while loop as soon as that button is pressed. So if you just say while RB0 with a semicolon, that's going to be a hard wait. You don't want to do a for loop here, because you don't know how long you're going to have to wait. I could sit there and not push the button at all, or I could push the button right away. And so what I want to do is just have it wait, and then you can output to the second line and write the button pressed. So that's what we'll do. Oh, really? Okay. It may be doing that largely because you're assigning something, but that pin is configured as an input. And so really assigning something to what is configured as an input doesn't really work. Yeah, you don't want to do while RB0 equals 0, because you want to wait until it is. If you do while it is equal to that, then it's just going to run once and it'll fail that while conditional, and then it will go away. Does that make sense? No, you're just going to leave that on the top line. So I've actually written this. I'm going to put this. I'm going to put it off screen, and I'll program my board to do this part of the lab real quick. So I'll leave you in the dark for just a moment, and I'll replace my main. And then I will program it. So I'm programming it right now. And I'm going to go ahead and put that up on the screen. Okay, so what it should look like is something about like this. So I say press the RB0 button, and it's just waiting, 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 waiting. And then right here, this is the RB0 button, the bottom one. And now it says thank you. So there you go. All right, so that's what your second file should look like. So it's just a little while loop right there. Okay. So those are the two things for LCD. And then what I want you to do is get into some analog to digital conversion right here. And so you can review those registers. This says, what would you need to enter in the following registers in order to perform an analog to digital conversion on AN0, which happens to be the same pin as RA0, with the results left justified, sampling at a rate of FOSC divided by 8, with the boundary voltages as VDD and VSS. That is your +5 and your ground. And show the entries in binary prior to setting the go bit. So remember, we turn on our A to D module, we get everything set up on the channel, and then we set the go bit to say go ahead and do it. The reason we do that is you want to set up the channel and have all those bits set. If you're setting the go bit at the same time that you're setting exactly which register or which pin number that you want, you could have what's known as a race condition. I think we talked about that a little bit in the digital class last semester. And effectively, you don't want it to be trying to settle which channel you're trying to collect from at the same time it's trying to actually do it. Allowing it to settle and then saying go allows that to work. So that's what I want you to do in number 3 is just figure out, okay, what do I need there? Of course, in AND cell A, you want that corresponding bit to be set up as a 1 for analog, all the other bits 0 for digital, and then tris A, that particular pin needs to be an input if we're doing an analog input. Now, this part 4, I did not explicitly go through exactly how those results come back in terms of the A to D, but you should be able to surmise that. But I want to go through that very briefly in our last about 15 minutes here, just to make sure everybody understands how the A to D calculates its values. So let's go through some examples of that. So in this case, I said if you were to digitize 3.3 volts, what values would you expect in the ADRESH and ADRESL? And in this case, we're going to digitize that assuming that you have between 0 and 5 volts. And remember, we have a 10-bit analog to digital conversion. So if you go through the successive approximation like I talked about in class or in the online lecture, what you can do is realize, okay, I've got these various different bins that I can sort things into. So if you had something as simple as a 2-bit analog to digital conversion, you would see, okay, 0, 0 is going to be in this leftmost bin. So that's going to be anywhere from 0 to the full scale voltage divided by 4. So if you're talking about between 0 and 5 volts, then that would, for the full range, then this would be between 0 and 1.25 volts. Then the next bin is between the full scale over 4 to the full scale over 2. Then the next bin, full scale over 2 up to 3/4 of full scale. And then the last bin is the last fourth of the range. And so you can actually figure out which bin you belong in by realizing, okay, what are the bin ranges going to be? And you can go through and do a successive approximation by saying, all right, for my first bit, am I more or am I less than half of the full scale? So if you're talking about 0 to 5 volts, you ask yourself, okay, am I more or less than 2.5 volts? And in this case for 3.3, you would be, and you would put a 1 in that first bit. And then you would go through to each next bit with the next bit, the next bit, the next bit worth half as much. Okay? So you can do that for the 10 different bits that you have. And then just remember, if it's left justified, the most significant bit is all the way to the left in the ADRESH. That's the analog to digital result high byte. And it goes all the way through to the first 2 bits in ADRESL, and then you're padded with zeros on the bottom end. If you're right justified, the exact opposite is true. The leftmost 6 bits in ADRESH are padded with zeros, and then you go through and you put the results starting with the top 2 bits going in the bottom 2 bits of ADRESH, and then the least significant 8 bits are in ADRESL. So that's what you should be able to compute for that part. So you can manually do it bit by bit by bit, but you can also realize sort of what the range is. So I wanted to show these calculations here, in that each bin has a range of voltage from whatever the binary value is for the analog to digital conversion value divided by 2 to the n times the full scale voltage. So here's another example. Let's suppose we had a 4-bit analog to digital conversion, and we are going between 0 and 5 volts for our range here. And the value that we got out of our A to D was 1100. Well, 1100 is binary for 12 decimal. And so I can figure out what that voltage is by basically back solving this formula and saying, okay, well, I have 12. 12 divided by 16, that is my 2 to the n. So in this case, I have 4 bits, so my n is 4, 2 to the 4 is 16. If I multiply that by my full scale, that is the lowest voltage that I could have in the bin. And then if I go to one more than that, so 12 plus 1 gives me 13 divided by 16 times 5, that is the highest end. So that means if I got 1100 out of a 4-bit A to D, then the range that I have is somewhere between 3.75 volts and 4.0625 volts. And so you can do the same thing. That's effectively what you're going to need to do in the last problem on the worksheet. Let me show that. Is if you got this value in your ADRESH and ADRESL, what will be the range of voltages that you would be able to represent? So in this case, you've got a 10-bit A to D, and so your N is going to be 2 to the 10 or 1024, and then you can figure out, convert this hexadecimal value to a full-scale binary value, take that, divide it by the 1024, multiply it by the full scale. That's going to be your minimum. Then take that value, add 1 to it, divide it by 1024, multiply it by 5 volts. That would be your maximum. So that should tell you what the minimum and the maximum voltage should be there. Okay? So are there any questions about how to get out the computation of the analog to digital conversion value, or how to get out the voltages here? Okay, so hopefully everything's clear in terms of what you're expected to do. I realize I took almost your entire period and you don't have a lot of time left to do the in-class exercise, but that will turn into a homework or the next 5 minutes kind of exercise. The other thing that I will mention, and I will post this assignment later today, is what we're going to do is do some analog to digital conversion, as you might expect in the lab tomorrow. So what we're going to effectively do is take an analog voltage off of the potentiometer that we have on this board. So down here, this little potentiometer is connected to AN0, and it can provide an analog signal that we could digitize, and we're going to display some information about that voltage on the LCD. So that's what we're going to do in lab tomorrow. So I'll post that assignment a little bit later today. So just be prepared to do that tomorrow during the lab.
You are now muted. You are now unmuted.
Are there any questions I can answer for anyone? Okay, well, I hope this was helpful to you. I'll stick around here if you have any questions as you start going through the exercises. But we've got another about 4 minutes, and I'll hang out until then. If you have any questions, feel free to put them in the chat, or you can turn on your microphone and ask to the course. And if there are none, I will see you guys tomorrow, 10 a.m., and we'll go through the lab where we'll put out the analog to digital conversion value on the top line of the LCD, and then we'll put out the voltage on the second line of the LCD. So I will show you how to do those calculations in that lab assignment. All right. I hope everybody has a great rest of your day.
You are now muted. You are now unmuted.
Oh, and I will post the recording of this to the Canvas site as well, so you'll be able to have this this entire video lecture.